When Kalman momentum integral equation, drag force is a force which is feel in the flowing fluid. This is u infinity is equal to 0. This is mu is not equal to 0. Then this is positive x. These are the arrows. These are the dots. This is negative x negative. Tau is equal to mu into du by dy. Y is equal to 0. Drag force is equal to tau naught into a. Implies Ft is equal to tau naught into a, which is skin drag. Total force or drag force. Then this is drag force due to pressure or pressure drag. Skin drag or skin friction drag. Then this is Pa. This is Pa cos theta. This is Pa sin theta. Pa cos theta is the pressure drag. This is airflow. This is minimum resistance. Direction of drag force. U infinity is equal to 0. Then this is arrow. This one is arrow U. Fd is equal to tau naught into A. These are the arrows. U is equal to 0. Then this is Fd. This one is Fd. Here is the line. Direction of drag force is along the direction of motion of fluid. U infinity. These are the arrows. X equals 0. X dx U delta. Then A B C D. This is U infinity. This one is x is equal to L. This is dx. This is dy. This is y. This is A B C D. This is U. This is delta. Focus on it. Then this is B. Then this is dy. Then dA is equal to B into dy. Drag force on the plate dFd is equal to tau naught into bdx. Integration from 0 to fd dfd is equal to integration from x equal to 0 to x equal to L tau naught into bds. Total skin drag on the plate u dy y A B C D delta. Focus on it dx. dmBC is equal to dmAD plus curl by curl x dmAD into dx. Note here. Note this diagram. This is A B C D. BC greater than AD. BC greater than AD. Mass flow rate from BC. Mass flow rate in the element is equal to rho into bdy into u is equal to rho into u into bdy. The mass flow rate from BC is equal to mass flow rate is equal to integration from 0 to delta rho into u bdy from AD dmAD. Mass flow rate from at x plus dx from the leading edge. Taylor series integration from 0 to delta rho into u bdy plus curl by curl s integration from 0 to delta rho into u bdy into dx. Then this one second my first dm cd dot is equal to curl by curl s integration from 0 to delta rho into u bdy into dx. Momentum flux from AD is equal to integration from 0 to delta rho into u bdy into u is equal to integration from 0 to delta rho into u square bdy. This is third. Momentum influx from BC is equal to integration from 0 to delta rho into u bdy plus curl by curl x integration from 0 to delta rho into u bdy into dx is equal to integration from 0 to delta rho into u square bdy plus curl by curl x integration from 0 to delta rho u into bdy into dx. Momentum influx from CD is equal to curl by curl x integration from 0 to delta rho into u bdy into ds into u infinity. Net rate of change of momentum in ABCD or AB is equal to momentum influx from BC minus momentum influx from CD minus momentum influx from AD is equal to curl by curl x into rho b is equal to into integration from 0 to delta u square minus u into u infinity into dy into dx is equal to curl by curl s rho b is equal to integration from 0 to delta u square minus u into u infinity into dy into dx. dft is equal to tau naught into bds. v vector dfd in the direction of rate of change in momentum is equal to minus tau naught into bdx minus tau naught into BDS is equal to curl by curl x into rho b into integration from 0 to delta u square minus u into u infinity into dy into dx implies tau naught into b dx, b and dx get cancelled, is equal to curl by curl x into rho into is equal to into integration from 0 to delta u into e infinity minus u square into dy. Tau naught is equal to curl by curl x into rho in integration 0 to delta u infinity square into u by u infinity minus u square by u infinity square into dy into dx. If fluid is incompressible, rho is equal to c. Tau naught is equal to rho u infinity square into curl by curl x into integration from 0 to delta u by u infinity 1 minus u by u infinity into dy, which is momentum thickness theta. Then tau naught then implies tau naught is equal to rho u infinity square is equal to curl theta by curl x, which is laminar, turbulent and transition flow, which is when Kalman momentum integral equation. Boundary layer thickness delta is equal to fx. For boundary layer thickness, for note here, for boundary layer thickness delta is equal to fx. Velocity distribution should be given. U by u infinity is equal to this bracket. Then step first, use when Kalman equation. Tau naught by rho u infinity square is equal to curl theta by curl x delta dash 1. Theta is equal to integration from 0 to delta u by u infinity 1 minus u by u infinity into dy, mostly delta. 1 implies tau naught is equal to dash equation of tau naught. Step second, Newton's law of viscosity. Tau is equal to mu into du by dy dash 2. Wall shear stress tau naught is equal to mu into du by dy, y is equal to 0. U by u infinity is equal to dash. Then implies u is equal to dash. Then du by dy is equal to dash. Then put y is equal to 0. Du by dy, y is equal to 0, equating 1 and 2. Delta is equal to boundary layer thickness. Local and average are coefficients. CDS local, CDL or CD bar average. Then this is x, this is a. CDL or CD bar. CDX is equal to tau naught by half rho infinity square. Half rho infinity square is the dynamic pressure. CDL or CD bar is equal to FD by half rho u infinity square into a. Note here, this is a, this is b. Length is equal to a, length is equal to b. Blouse's solution. For a laminar flow, boundary layer thickness delta is equal to 4.91 x by under root rex or 5x by under root rex. Average drag coefficient CD or CD bar is equal to 1.328 over under root REL is equal to FD by half rho u infinity square into A. Blouse's solution turbulent flow, u by u infinity is equal to y by delta whole raised to power 4, n is equal to 1 by 7 if 5 into 10 raised to power 5 less than rex less than 10 raised to power 7. Boundary layer thickness delta is equal to 0.37x by under root by rex raised to power 1 by 5. CDL or CD bar is equal to 0.072 over under root REL raised to power 1 by 5. Then CDL is equal to FD by half rho infinity square into A. Then this is u infinity, this is x1, x is equal to 0 leading edge. Then this is transition, this is trailing edge, x is equal to L. This is laminar flow, this is transition, this is turbulent flow. Rex is equal to rho u infinity x by mu. If REL greater than 5 into 10 raised to 5, we must calculate transition point. If REL less than 5 into 10 raised to 5, flow is laminar, flow throughout the plate. Then Rex is equal to RECR, which is critical Reynolds number. Rho u infinity x by mu is equal to 5 into 10 raised to 5. Let x is equal to x1. Length up to this is laminar. Then x is equal to 0, x1, laminar, x is equal to x1, L minus x1, x is equal to L. This is turbulent. Calculation of total drag force L. Step first, consider throughout the plate as turbulent flow. X is equal to 0, x is equal to x1, x is equal to L turbulent. CD bar is equal to 0.072 by REL whole raised to power 1 by 5 is equal to FD square by half rho u infinity square into A. FD implies x is equal to 0, x is equal to x1. CD bar is equal to 0.072 REX1 or REX1 raised to 1 by 5 is equal to FD by half rho U infinity square into AX1. FD1 is equal to drag force in turbulent zone is equal to FD minus FD1 dash 1. Drag force in laminar zone CD bar is equal to 1.328 over REX1 raised to 1 by 5 is equal to FDX1 over half rho U infinity square into AX1. FDX1 is equal to dash 2 drag force due to laminar FL. Total drag force is equal to 1 plus 2. This is FDX1, this can be FDX1, then this is FD minus FD1. 1 plus 2. FD laminar or FDAB for laminar zone. CD bar is equal to FD over half rho U infinity square into A is equal to 1.328 over under root REQ, which is 5 into 10 to 5. FDAB is equal to, then this one is the numerical part. Okay, this one is the numerical part. This one is the numerical part. Boundary layer separation. Then this is A, B, C, D. X, A, UB greater than UA. Then this one is the line. This is U decreases, K current density decreases. This is away since friction do not overcome. dP by dx less than 0, which is pressure gradient. Then this is U infinity. This is A, B, C, D. These are the diagram. Current density increases, U increases, implies pressure decreases. When A increases, implies U decreases, implies dP by dx increases, implies current density decreases. When A increases, implies U decreases, implies dP by dx increases, implies current density decreases. If dP by dx less than 0, boundary is not separated. If dP by dx greater than 0, boundary is separated. If dV by dx is equal to 0, at this boundary is going to separate. When du by dy greater than 0, boundary is not separate and it will stick to surface. If du by dy less than 0, y is equal to 0, implies boundary is separated. Du by dy y is equal to 0 implies verge of separation.